Welcome back to the data science track, everyone. I'm lucky to get to introduce our next speaker, who's one of my coworkers. He's a software engineer at Databricks. Please join me in welcoming Joseph.
Okay, thanks. Great, so what I'd like to talk about today is combining the strengths of MLib, distributed machine learning and data analysis, with popular data science tools designed really for single machine analyses like scikit-learn, R, Python pandas, and so on. About me. I work as an Apache Spark committer at Databricks. My background is in machine learning, but with an emphasis on scalability. And so I guess when I was learning about ML, a lot of my background was in data science tools like scikit-learn, R, and so on. So can I get a show of hands? Like, how many people have used scikit-learn, pandas, or R? Cool, lots of people. Excellent. So the first things which come to mind when I think of these tools are like, for scikit-learn, like incredible documentation. Very easy to use, straightforward in terms of like examples, walkthroughs, and so on. So it's really easy to pick up and start using it. R, first thing I think of, are like tons of packages available for whatever type of model you would like, things like GLMnet, and so on. And so because of this sort of like ease of adoption and this plethora of packages, people think of these as sort of like these core great libraries with, and because of this, there's been a lot of investment, both in terms of education, both during school and in businesses, and in terms of tooling and workflows. And so because of this, of course it makes sense that people want to keep using these tools, familiar APIs, familiar sets of algorithms, and so on. But of course, nowadays, people also talk a lot about wanting to do big data. And to be able to do things like, say, train a topic model on all of Wikipedia, or say, be able to scale your workload just by adding more workers, being able to decrease the training time, get linear speedups. Another big use case is recommendation. There, it's really easy, you know, after you have a few million users, a few million songs or items you're trying to sell, to collect like billions of ratings in your data sets. And all these examples are, if you're interested, in blog posts where we have more details on the use cases. But right, in addition to scaling, part of what people are looking for with big data is the assumption that with more data, you can get higher accuracy, either just from the data itself or from being able to train more complex models. It's also important to think about big data in terms of scaling your business. You know, as your business grows, you have more users, you may have more data sources available, and you need to be able to scale your workloads, ideally not having to constantly retool. It's also really important to be able to integrate with production systems, and things like Spark sort of provide that already. A lot of integrations with existing databases and so on. But now we have this gap between the two. You know, at school, I learned machine learning using R on my laptop. And now this goal in production and business is to do machine learning on a huge computing cluster. And of course, you don't want to make this jump in a single leap. But how do you get from the single machine workload to a fully distributed one? So I'd like to talk about this, partly to demonstrate that it is useful to do this migration, but also that it can be done in a less painful way than you might otherwise imagine. And so what would a good wish list to start? First, it'd be nice to be able to move to that production environment, but keep using your original code. You know, if it works on your local machine, it should work in that production environment. And after that, you could start both linking to the production data sources and also slowly start distributing your workload. So yeah, we want to be able to use the distributed data sources. We want to be able to distribute the ML workload piece by piece. And this is partly so that you can do it lazily. You know, if you don't need to distribute something, why do it? But once you do need to, it should be easy to. And the other part of this, in order to facilitate these transitions, is we need to be able to easily switch between the local and distributed settings, in particular in going from distributed data representations to local ones and vice versa. And finally, I'd say in this transition, we'd like to keep familiar APIs, and that could mean, exactly the same method names or so on. It could mean similar algorithms where it may have a different API, but it has the same behavior you'd expect, or so on. So to talk through this wish list, I'm going to do a demo, basically. And I'll first start by explaining the task, start with a single machine workload, and then slowly distribute it. And what I'd like to do is try to keep coming back to this wish list and point out how we're overcoming these various pain points. So the task is from this Amazon reviews data set. It's available there. Basically, it's reviews scraped from Amazon, where there's a lot more metadata available. But here, I'll keep it simple and look at rating, which varies from 1, which is bad, to 5, which is good, and the review, which is just plain text. And so what I'd like to phrase as our problem is sentiment analysis. We want to be able to look at text and tell if the person is happy about the thing or not happy about it. So we'll take a text and predict the user's rating. Cool. So our basic ML workflow that we're going to do is start with the text and rating. Here, it's about a scarf, rating 3. I actually made this one up. But we'll start by tokenizing it, which is just going to take the text and break it into individual words. We're then going to take those words and put it through what's called a hash term frequency featureizer, which, if you're not familiar with it, basically hashes this to a feature vector, where the point is, ML algorithms like numerical vectors, and so we're going to give them one. Then we'll use a really simple model, linear regression, where we'll train it on these features and try to predict that label. So at the end, after we've trained this linear regression model, we'll be able to give it new text, pass it through this workflow, and get a prediction, such as rating equals 2. Cool. So very simple workflow. But the point is, as you scale it up, either more reviews or larger model dimensionality, you start to hit bottlenecks in your workflow. Cool. So the other part of our workflow, here's sort of a simplified view where I've mushed 2 parts together into feature extraction and then linear regression, the model training. The other part of our workflow will be model selection, or parameter tuning. So we're just going to look at one parameter, the regularization for linear regression. And if you're not familiar with it, basically it's a parameter you can tweak for linear regression, which can affect how well it does when making predictions on new, unseen test data. And so a common practice in machine learning is to test a number of regularization parameters, and to do this using what's called cross-validation, which is essentially where you split your data into multiple groups, you train on some groups, test on others, and then shuffle and rotate around these. So that you essentially end up training one model, training another, and so on. And then at the end, what you're going to do is be able to pick sort of the best linear regression model, which will correspond to the best regularization parameter. So this is kind of the setup we're going to begin with. First just in scikit-learn, and eventually just in MLib. Cool. So I'm going to try to do this demo. And starting out with one machine. So, okay, sorry, it's stopped. It started mirroring again. Let me try to fix that. Good. So we have our workflow here, and these single little red things are just to indicate we're running on a single machine, first feature extraction, and then cross-validation. So I do some imports. I'm defining going to make this larger in hopes that that'll make it easier to see from the back. But I'm defining just like a little results collection, which I'll use to keep track of stuff as we go through our workflow. Cool. Gonna load data, and we'll come back to that later. But basically what I've loaded here is a Python pandas data frame, and it has the rating and the review text. Cool. So what we do if we were doing stuff in scikit-learn would maybe be first say, how many reviews do we have? So we can count them. We have some 20,000. And then we could say extract the reviews and ratings from the data frame. And then we're ready to pass this to scikit-learn. So by the way, if the Wi-Fi conks out, I'll go through a static version. At times it was giving me long pauses in this demo earlier. So what I'm doing here is defining this scikit-learn pipeline. If you're not familiar with it, basically, I'm specifying sort of the 3 elements for feature extraction and then training linear regression. Here, less so because of the type of regularization I'm using. But at any rate, I'm defining that pipeline, which I was showing graphically earlier, and then a set of 3 parameters to sweep over. Cool. And then in scikit-learn, you would take, say, grid search CV, which is going to do cross-validation for you, where you pass it the pipeline, the parameters to test, and the number of what's called folds of cross-validation to sweep over. It fits on that, and then we can get the best result back. So what this is doing is we have 3 folds of cross-validation, 3 parameters to sweep over. In other words, we're training 9 linear regression models. I'll choose the best parameter, and then I'll refit using that parameter on all of the data. So this takes a while, 10 models to train in total. Took, what, 26 seconds. Not that long, but didn't want to make y'all sit there. Cool. And so then what I'll do is evaluate this using what's called R squared. If you haven't used it, basically 0 is bad, 1 is good, and larger is better. So it's data dependent, but at any rate, right now we're getting a score of 0.14. But what I'd like to show now is this is your basic, scikit-learn workflow. But what I've done here is hidden some of the data integrations. So the first thing we said in our wish list was to be able to run in a production environment. So I'm demonstrating this in Databricks, which does give you easy access to production data sources. And that's the first thing I would like to show. So here, actually, these file paths are mounted S3 buckets on Amazon S3. And I'm loading from a Parquet data file. That's a distributed data format using a columnar store. And then I'm using the first of our integrations, where Spark data frames provide a simple toPandas call to convert this to a local pandas data frame. And we can go down to the end of our workflow and use this same sort of integration, but in reverse, where we want to evaluate on test data. We could say load a test data set from S3 and convert it to pandas, and then compute the test R-squared metric on it. We could also use this to say, after doing productions, export them to a distributed format for another team to pick up. So here, what I'm doing is making predictions using the scikit-learn model, converting that to from a pandas data frame, into a pandas data frame. And then after scikit-learn is done making those predictions, what I'll do is, actually this pausing here means that the Wi-Fi is being a little iffy. So what I'm going to do is switch to a static version of this, where I've already run this, and point out, basically what I'm doing is making predictions using scikit-learn, saving those as a pandas data frame, and then converting that into a Spark data frame so that I can use Spark's distributed data sources. Here I'm saving it out to JSON in another Amazon S3 bucket. Cool. So that was our basic workflow. And the main thing I'd like to remember is that this took 26 seconds here. I think it was 28 in the other workflow. But what I'd next like to do is the obvious thing, which is scale this up by distributing cross-validation. And so what I'd like to point out here is that it's very simple to distribute. Basically, you're training 9 models, and it makes sense to do that in parallel using scikit-learn. And what I'm demonstrating here is actually a package we're putting together and are about to release sort of an alpha version of, where rather than importing scikit-learn's grid search CV, I'm importing it from this Spark-based package, pdspark, and everything else has remained the same, except that down here, grid search CV now takes a Spark context so that it can parallelize these tasks, and it's returning a pdspark instance, but you can get the scikit-learn grid search result like this, and then everything else in our workflow is remaining the same. But the critical thing is now, we've cut our training time down to 8.7 seconds, where that's essentially because we've parallelized training 9 models rather than doing it sequentially. Cool, so, and you'd see even larger speedups if we are working with a larger task. Nice, so that could, get us a bit farther. But then the other part of our workflow, I guess, is feature extraction. So here we were doing it on a single machine, but we could distribute it. And essentially what we were doing before is operating row by row in our data set, taking that text and munging it into a feature vector. And in this demo, it's a very cheap operation, but in practical workflows, this can often be an expensive part of your process. So what this notebook is demonstrating, and these will be posted online later, is taking this feature extraction and actually doing the feature extraction using Spark. So what I've done here is load the data, leave it as a Spark data frame, and in the distributed feature extraction part, I'm using analogous featureizers as scikit-learn, but the Spark distributed version. So they likewise have where you can fit on the distributed data frame, transform it to get your featureized data. After that, we're left with a Spark data frame, but need to pass that to scikit-learn to do that final cross-validation step. We can convert a Spark data frame to pandas, again using this pdspark package, where the main issue is that what we need to pass to scikit-learn is not a set of just arrays of numbers, but actually a scipy type, if you're familiar with it. So basically, we provide data type conversions in this package, and after this, everything else remains the same in our workflow, where we train a scikit-learn model, where now our model is simply lasso without featureization, and we can fit it using distributed cross-validation, and so on. Cool. So what we did up to now is distribute feature extraction, cheap in this demo, but very expensive in some cases in practice. Collect that data to a pandas data frame, and then distribute the task of model training, where each of these models is being trained locally on some worker. We can imagine as you scale up further, and this happens in the live demo when I have better Wi-Fi, but if you increase the size of the data set, of course, it takes a long time to train models on a single machine. So it brings us to sort of the final workflow, which is to distribute everything. Essentially, we keep feature extraction distributed as before, but next, we're going to distribute each of the training of the linear models. And so to do this, all we're going to do is come down to this critical element in our workflow, where we're defining a Spark pipeline. So there's the same pipeline we saw before. We tokenize to produce words instead of text. We do hashing TF to translate those words to a feature vector. And then we call linear regression, which is going to train that model. So we are phrasing that as a Spark pipeline, and then we need to do that grid search. So now rather than using the scikit-learn grid search CV, what we're going to do is build a parameter grid in a similar way. Here we're using the same regularization parameter values as before. And then we're going to define an evaluation metric, which will be set to r squared, which is the same thing scikit-learn was using. We then pass it to what's called a cross-validator rather than grid search CV. But it's intuitively the same, where we specify the estimator being this pipeline, an evaluator, and a parameter grid. And then we fit it. And so this was done on 10 times as much data. It took about 5 times as long. But basically, as you scale up, the benefit of distributing becomes like greater and greater. Cool. So after we fit, we essentially have a Spark model which can easily operate on distributed data. And so scrolling down to the end of my little demo, what I had done was load, instead of 4,000 test instances, load 4 million and evaluate on that 4 million row data set. Cool. So also, over the course of this, if we had watched some of the r squared scores, we'd seen they started out at like 0.14, but increasing the size of the data set like helps significantly and takes us up to now 0.36, significantly better. Cool, so just to recap, what we've done is, seen this slide before. All right, but what we started with was doing this workflow on a single machine. We then distributed cross-validation, where this gave a critical jump in the performance of scikit-learn. If then we had a bottleneck in, say, featureization, we showed how we could distribute it using Spark and then keep our existing cross-validation workflow in scikit-learn. And then finally, we moved completely over to Spark, where we distributed both featureization and the training of each of these linear regression models. Cool. So as far as improvements that we observed, first, we saw faster model selection for small data, where we distributed cross-validation. I didn't have time to show it in this demo, but there's much faster training for large data. Like training on that 10 times larger data set with scikit-learn would take way too long for this demo. And then finally, showed that we could get better predictions, r squared, with more data. I'll also note in practice that these problems like become, with scaling, are much more exacerbated if you follow proper procedures. First, you'd probably do more than 3 folds of cross-validation, depending on how much data you have. Second, you'd likely tune more parameters. Here I was tuning 1 parameter with 3 possible parameter values. In practice, you might have many parameters to tune, many more values, and distributing that task could be much more beneficial. And finally, it's natural to increase the model size as the data set size increases. If you have more data, then your model can be more expressive. But all 3 of these things are just going to exacerbate the problems as you scale if you stick with a single node. But what I'd like to emphasize is that you're able to overcome each of these bottlenecks incrementally. Cool, and so finally I'd like to mention sort of the integrations that we touched on. First, access to distributed data sources. That comes pretty naturally, both in terms of conversions between pandas and Spark, conversions between SciPy and MLib types. That was part of that Spark package, which should be released soon. Distributed model selection. This is very doable just by hand, but for the sake of convenience, we're also providing this in this package. distributed ETL, or featureization, which we were doing when we moved that first part of the pipeline into Spark. And finally, distributed learning, when we moved everything into Spark and MLib. And one thing I did not mention yet, but where we have initial versions in this Spark package, are conversions between scikit-learn and MLib models. So you may train a model in either, and then deploy it essentially in the other framework. So, cool. I've focused a lot on scikit-learn and Python pandas, but I do want to mention integrations with R. So data frames are the first thing which were added in 1.4, and essentially add a couple critical components. They allow for conversions between R local and Spark distributed data frames, as well as SQL-like queries from R. If you're not familiar with the R data frame framework, basically, the API is designed to be very intuitive for R users, but to allow you to do these data frame operations on distributed collections. And then 1.5, we introduced an R-like MLib API for generalized linear models, where you could make a call like this, looks like a normal R call to GLM, uses our formula and so on. But really what this is doing is operating on distributed data frame and calling into the distributed Scala implementation. Cool, so if you wanted to repeat this demo at home, sorry I couldn't go through it live because of the Wi-Fi, but essentially use Spark 1.5, this Spark package, which will be released soon, and the code will be posted online. I also want to mention this Sparkit-learn package, which is another package doing PyData integration with Spark. And it has also a really nice API for familiar, which will be familiar to scikit-learn users. And the reason that we're kind of operating in this separate Spark package is that we're using some more experimental and developer APIs within Spark, which we don't want to, expose. So I also want to mention, if you want to try the actual notebooks, which will be posted online, then you can try them on Databricks with a free trial. Cool. And so finally, what's next? First thing that's going to happen is further work on these integrations. For Python, what I'd really like to do is be able to support more models and data types in these nice functionalities of distributing cross-validation and of converting between MLib and scikit-learn models. For R, there's ongoing work on expanding GLM formula, such as to include feature interactions, and also to support calling into other MLib model types from R. A real goal as we do this is to try to match features and behavior. You know, even if you have to modify like the name of an algorithm or whatever, it's really critical to have the same expected behavior, the same sort of functionality as you do this workflow migration. The final thing I want to say, which is to do next, is to get involved, either contributing to Spark or Spark packages, and also providing feedback, especially about prioritization in terms of what elements of these scikit-learn pandas are workflows are really critical in these integrations and where it could be improved. Cool. So with that, I'd like to say thank you very much and leave some relevant links here for Spark, Spark packages, and Databricks. Thanks a lot.
Thank you, Joseph.